If you've used large language models, you've certainly encountered the fact that sometimes they will respond with an answer that doesn't match with your understanding of the way reality is. So these hallucinations are common, and they also occur perhaps even more so when working in a technical field like chemistry. So I want to talk about the origin of these hallucinations, provide some tricks in how to avoid them, but then also dig into a very specific method that we recently published in the Journal of Chemical Information and Modeling that I think points the way towards a systematic method to reduce hallucinations for a lot of different applications. And so we'll get to that after some background. So one of the favorite hallucinations that some students in my lab found are these chair and boat conformations of cyclohexane. So these would not do well in an organic class. And if you aren't aware of it, you should be aware that in addition to these visual hallucinations, there's also a fundamental poor ability of large language models to handle basic math, even addition. So a long enough, complicated enough math equation, or simple but long, will often result in an incorrect answer. And the origin of that has to do with the method for training large language models. So these are based on a transformer architecture, and they simply predict the next word or the next token. So they're trained on large databases of language, and they become very proficient at guessing what the next most likely word is and returning those probabilities. Um, but that's the reason part that they don't understand math, because if they've encountered a specific equation like 2 plus 2 equals 4, they will be able to regurgitate that, but that doesn't indicate a deeper understanding of the underlying math, which is where the math errors come from. So the problem gets worse in looking at chemistry. Beyond the simplest chemicals, it's not easy to have a single simple word representing a chemical. There's many different systems for human readable chemical naming, but also for naming chemicals within computer science and databases and websites. It's necessary to have simple methods. So one developed for that purpose is SMILES. And here, the SMILES for cyclohexanol is shown, and it's used in the URL to look up the information about that compound from PubChem. And it's a relatively simple one. There's 6 carbons for the 6 carbons of the ring, and one on the first and sixth carbon indicate a connection that completes that ring structure. And the parenthetical oxygen is an exocyclic OH group. So there's plenty of SMILES codes available in web scraped data that's probably been used in training most LLMs. So if you look at a Wikipedia, you'll find many SMILES codes. And therefore, if you ask questions that match to that, so here I asked a GPT for a specific property of a chemical butanol using the same representation of the SMILES code from the Wikipedia article, I get a precise and accurate answer. But that's really the exception. When you get to more complicated, not even as complicated as the one I'm showing here, molecules, you'll often find errors. And so here I took a SMILES code for a complicated molecule that couldn't exist within the large language models training data and asked for a summary of the functional groups and found significant errors. One of the problems comes from how language is tokenized, and these tokenizers for many of the open models and even the closed models can be found. So for example, at this URL, you can look at how OpenAI's tokenizer works, and you can see that it works very well with language. So sentence in English text is tokenized very readily. But a chemical structure in the form of a smiles code isn't handled as well and is chopped up into very small units, which aren't going to accurately keep and convey information about that structure. Things like rings are separated by many tokens within there. So it's not a surprise then that GPTs hallucinate when asked questions about chemical structures. So for example, if I give it a chemical structure, even of a common chemical, and ask for an image with all the sp3 hybridized atoms colored red, the GPT response is not remotely accurate. And this is also related to the image generation methods that probably don't have a lot of chemical structures in their training data. So on the right is a pretty good answer, and that comes also from GPT, but using a GPT assistant that I created and called Molecular Informatics Code Helper. The URL for it's up top, and the reason this works is because it's not using the image generation abilities of the DALL-E model to generate the image, but rather if you load this assistant and click the first box on the left, these assistants can have documents stored for use by the assistant. And in this case, what I've included is, in addition to some text documents that explain things like smiles codes, I've also included the package that's necessary to provide chemical functionality to Python. So Python runs in the background of these assistants instances such that if you click on this button within this helper, you'll get an accurate understanding of any smiles code because you're no longer limited by the training data. These are easy to create, simply allowing code interpreter in the options and providing conversation starters and then including documents like I mentioned. So in any use of AI, it's probably good to compare the different AIs that are out there and whether they meet your needs. There's no shortage of metrics, and they become obsolete over time. They become saturated. They can be cheated. But most importantly, if you've got a specific task you want to do with an LLM, you're better off using your own assessment. And so in this case, I'm just checking what various LLMs do with request for drawing of a smiles code. And I can tell from this that Claude 3.7 Sonnet has probably a decent amount of chemical structure drawings in its training data, but it's not parsing the smiles code particularly accurately and failing to show aromatic rings properly, but not doing horribly overall. I'm not sure where Grok 3 is going, but that's what it provided. Gemini 2 from Google at glance looks good. The text, though, is hallucinatory. And then if you count the number of bonds on those carbons, you'll soon discover that it's pretty off base. A lot of them don't produce an image at all. The only one that works well, comparable to what I showed in the assistant on the previous slide, is from Wolfram. It's also a Chat GPT assistant. Slightly different method because they offload the work to their own servers, but the same result. They've got a chemistry knowledgeable GPT assistant. Unfortunately, both of these are only available through paid accounts with GPT.